Alright, so this video is going to be on the concepts of mechanical design in FRC. It's going to be a basic overview, hopefully to help you get started. Alright, let's jump into it. So in this presentation we're going to go over the design process, what you should and shouldn't CAD, different CAD techniques to help you speed up your CADing process, and a couple of design details. Alright, so what is mechanical design? Mechanical design is when you develop and communicate mechanically based solutions towards a set of project criteria while adhering to the appropriate constraints. What does this mean? Basically means you're working together to come up with a solution to a select problem where you have certain constraints that you have to follow. So these criteria are always going to be decided by how and what. So it's going to be decided by what you need to do and how you're going to do it. And this should always be your main focus. You should never look any further than these when you're starting. You should use only the resources that you are familiar with and comfortable with. Experiment with resources in the preseason and outside of the season, but during the season you should only use the resources that you're comfortable using in order to make sure that you have the best designs as you possibly can. This involves developing and communicating. So you have to work together with other people, because others are going to, when you have multiple designs being tested at the same time, you can see which ones are more effective, which ones are more efficient, and by communicating that and developing those, you are able to create the best design as fast as possible. Right. So mechanical design is the crux of FRC. This is what's gonna make or break your season. If you start out with a bad design at the beginning of season, and you're 3 or 4 weeks in and you realize, oh, this design's not gonna work, that's a lot of time wasted. That's a lot of time you have to restart from. It's always best to figure out a solid design as fast as possible in order to get your robot to its maximum potential. So the design process, we'll go back to the what and the how. So you should decide on the first few days of kickoff what the objective of the game is. So whether it's picking up a ball and shooting it, or picking up a tote and placing it somewhere, you got to figure that out. After you figured out the what, start thinking about different approaches of how you could do it. If it's like picking up a ball, oh, we could shoot it, we could place it, this enables you to start designing towards a specific challenge. And I feel as in the first week, you should have your drivetrain completely decided and already started working. Select a drive base that's going to be viable for that game, and that's going to give you the best geometry to fit all your mechanisms together. Alright. After you have done that, let's skip one. Alright, prototyping. So after you decided on all these things, split up into 4 to 5 different groups and start prototyping different mechanisms. Some of the less important ones you can have one group, and for the more important ones you can have several. So this is So like say there's an intake. Intakes have been done hundreds of times before. You probably only need one group working on that. But like having different types of shooters, testing out if a double flywheel or a single flywheel works better for that specific game. That's where you would have multiple teams working on one design. You want constant feedback in parallel to the design. So you want to be designing, testing, and then figuring out if it works, if it doesn't. And then you want the design team to be aware of this progress so that they can change their designs, send in the new prototypes, get those tested, get all the problems figured out as fast as possible. Fail faster, fail as early as possible so that you are not stressed out later in the season trying to figure out a problem that came up earlier in the season. Make sure prototyping is aware of the constraints set by the design team. So if it can only be a certain height, if the shooter can have a specific angle, if the intake can only be this amount wide, make sure the team that is prototyping is aware of these constraints while they're doing it, because if they're out of the constraints, then the prototypes are basically useless to the design team. All right, once you've finished prototyping, it's time to transition towards CADing. So once the design team sees that the mechanisms can fit together, it's time to start connecting the teams to work towards making one complete robot. Continue gathering data until the prototype doesn't become useful anymore. Basically, keep, even after you've created the first version of your design, that's still a prototype. You still keep seeing if you can edge out something better, if you can place something somewhere else and it'll improve the performance. Always be grinding, trying to get the peak performance you can out of your robot. Design team needs to learn that mechanisms need to do. So what did I say here? Oh, okay. Design team learns what the mechanisms need to do, and then they begin to design them in 3D CAD. So once it's been decided how the game is going to be played, which prototypes, which designs work the best, you can start CADing those models up and getting them ready to be manufactured. Some details are things like, how do the totes stick into the robot? How much pay attention to the details, such as things like how much does the tote stick into the robot, or how much clamping force does the intake need to grab the tote, or like how much compression does the intake need to bring in the balls, things like that. Things not to CAD. For the first pass, you want to aim for fast iterative design. So you want to get your first designs out as fast as possible. You want your first robot to be done by week 4. Only CAD as much as you need. Just do basic rough CADs estimation off space, and then prototype those, and then work towards final iteration. So engineering isn't about being exactly on. It's about being as close as you possibly can. Just being close enough, And CAD gives us the ability to be close enough. Alright, so some CADing techniques for this are Crayola CADing. So this is where you sketch either a top or a horizontal view of the specific geometry that you need. This can be really useful in prototyping because you can just test to see what geometries you need, and then just create a rough prototype out of hand sawing wood and match drilling things together. And once you have figured all those things out, you can create your final design, but make sure your final design is malleable based off of that Crayola CAD sketch, so that when you change one value in the sketch, you can fix your entire design. For when you want really detailed CADs, a couple time savers are using half-inch hole patterns. What this does is it allows you to mount gussets really quickly. You don't have to worry about extruding different holes everywhere. You already have your holes extruded, so you just place your gussets onto those holes from the whole pattern. Using the mirror tool, pattern tools, when designing everything in one sketch. So the mirror and pattern tools are really useful when you have symmetric, when you either have symmetric assemblies or parts, or when you have long pattern parts or assemblies. You should try and aim to keep most of your mechanisms symmetrical for the mirroring capabilities. There's also the replicate tool, where if you have something that is replicated, a mate that's replicated in a bunch of different places, then you can place it, you can select the face with a bunch of different holes and it'll replicate that same mate everywhere. And you want everything to be based off of one sketch. So that way, if you change one dimension in the sketch, everything updates by itself. You don't have to go through and change every different part studio to get a different dimension, because that's just hassle. Skip fasteners for the first round. You definitely don't need them. When you're trying to get unless you need renders, you don't need fasteners in your CAD. They lower performance. They're just a pain to place. Just decide what needs to be CAD'd and what doesn't. What you can live without. And make sure to check if anything is interfering with each other, because if you go into the fabrication process and you notice these interferences, those parts that you fabricated, they become useless. You either have to shave them down, or you have to do something out of the ordinary with them, and that's not ergonomical. And then the most important thing is to practice. When you practice CADing, you learn. The key bindings become a lot more fluent for you. Everything becomes a lot more natural. So just practice doing these different CADing things, and you will see that you will get faster as time progresses. There's a couple different difficult parts and assemblies. So things such as things such as gearbox plates and gearboxes, drivetrain rails, like West Coast drives, belly pans, and gussets. So these are things that you are going to have in almost every single robot that you make. So for gearbox plates, one thing you can do is make sure that they're symmetrical. That way you can just mirror the sketch or mirror the mirror the part studio. That way you save yourself a lot of time. For drivetrain rails, same thing applies here. Make sure it's symmetrical, so you can just mirror it. In Onshape, there are feature scripts that allow you to convert rectangular prisms into tubes by just clicking on them. So that makes doing the West Coast drives a lot easier, but just mirror the sketch. And then belly pans, one of the hardest, probably individual parts to CAD. create, for those of you who want to create the rectangle and lay out the electronics first, and then you want to do the lightning in a lattice pattern in order to and just make the lattice as big as you need it to be to get it done as fast as possible. Just not too big that you have these long lines connecting the electronics holes, but using the lighting tool decreases the time for that immensely. And then gussets, there is the gusset tool now, which makes doing them a lot simpler. Definitely use that. So a major failure point is when there's too much material in some places and not enough material in others. So in places where you think there is not enough support, don't be afraid to reinforce it. But at the same time, if it's like a gearbox, you don't need to pocket it to be like a quarter of an inch. You can definitely get away with 0.15 pockets. So just keep that in mind. Alright, so something that's going to make designing a lot faster for you, designing your final robot, is just already getting your drivetrain out of the way from the get-go. So this can be done by just choosing a West Coast drive. So West Coast drive is simple. It's a cantilever drive where the shafts are pointing out of the tubes with a live axle. This means the axle is actively spinning. And 2976 abides by the 254 model, where you have a rectangle with either 6 or 8 wheels, 3 or 4 on either end. So like a tank drive, basically. It's a simple design, and it's not sensitive to tolerance issues. You can be a little bit make sure your deadlines are simple and not sensitive to tolerance issues. So you're not always going to be exactly precise with the CNC router or when you're match drilling things. So make sure you can accommodate for those issues. Using COTS gearboxes can save you a lot of time. So things like versaplanetaries, flexible design. So you want to use when you're transmitting power, you want to use chain or belt when things are too far away, because then you are able to change their distance easily by changing either the pulleys or the belt length. And then you want to use custom gearboxes to get the speeds that you want and the speeds that you need. And then consistent choice speeds up the design process. So you want everyone to be on the same page, everyone to be designing around the same central idea. And so, like I was saying, versaplanetaries, you can mount them on any motor, any ratio. Every motor on a robot, besides the drivetrain gearbox, basically, you can use a versaplanetary. Just don't put them under too high of a load. So a single versaplanetary is not going to be able to handle like elevator going all the way up. So make sure that they are in the right place in the right time. Fast iteration. You want to spend the least amount of time messing around with different numbers. You want to get your final design out as fast as possible so that you can test it, see where it fails, redesign it. Make sure everything is easily integratable. This is where the half-inch hole pattern comes in again. Make sure everything fits together. Make sure there's no interference. And so when you design things, by testing them, there's less time spent diagnosing these mechanical issues in the future. So some resources for understanding these things, for looking at some resources for understanding mechanical design is looking at other teams' robots. Steal from the best, invent the rest. So teams like 971, Symbotics, Greybots, and 1678, they all have their CADs public. You can view them anytime. There's on-shape links to them. Adam Hurd from 973 has his YouTube series, 973 Ramp, which covers a bunch of different topics, from linkages to gearboxes to elevators. I'll try to do a ramp series. I'll see if I get around to it. And then the different design calculators, they make designing a lot easier. So the JVNs or Copioli's design calculators, and using Chief Delphi, the public forum where you can see where other people are working on. Alright, I think that'll be it for this video. Just leave any questions that you have in the comments. I'll try to get to them. And that'll be all.